Right, here's a walkthrough video for the expected results table that we're going to use for our 4-bit add subtract circuit. The 4-bit add subtract circuit is going to be used in both Labs 5 and Lab 6. The first thing I want to tell you about, and this you don't have to know anything about this yet, but the reason I'm coming up with these particular test cases is I'm looking at when the result of 4-bit addition and subtraction could potentially give you errors in the sum register, and how we would account for those errors with the V flag and the C flag. All right, so there's a lot of detail there, and you don't need to know that yet, but I just wanted to let you know that there is a method to the madness here of figuring out the test cases. For example, I'm looking for examples where I have a positive number added with a negative number. Negative numbers are represented in 2's complement. And I get a result that falls in the correct range, right? So the correct range has to do with whether I'm looking at this as a signed interpretation or an unsigned interpretation. If I have signed numbers, the correct range would be that the output should be between -7 and, -8 and 7. We talked about that being the range for 2's complement representations for 4 bits. And if it's unsigned, the proper range would be 0 through 15. All right, so I'm looking at these different test cases to see whether something is in range or out of range. I'm intentionally choosing some things that would result in an out of range answer so that I can see what would happen with our circuit in this case and how do we interpret these things that we're going to call the carry and the V flag. All right, but our goal for Lab 5 is to just understand exactly the operation of the circuit. All right, we're going to come back in Lab 6 and spend a little more time on interpreting the results coming out of this add subtract circuit. All right, so for Lab 5, what I want you to be able to do is complete the expected results table in terms of the sum register, the carry flag, and the V flag. All right, so the sum register should mean something to you at this point because we're adding numbers together and we're getting an answer in the sum register. All right, but it turns out some cases don't give us the correct answer within the sum register because there's some overflow. And so we can detect those overflows with the V flags and the C flags, and we'll get into that more in Lab 6. So in the meantime, what I want you to be able to do is calculate the sum, carry, and the V flag based on the operation of the circuit. Okay, so I'm going to walk through a couple of examples of that, both for when the minus bit is set to a 0, so we're adding numbers. Okay, so we'll also do a case where m is equal to 1, where we're subtracting b from a. All right, so let's take a look at this first case. In the first case, I have the A register being 0, 1, 1, 1, and the B register is 1, 1, 0, 0. So I'm reading these off here. I'd like to be able to calculate what shows up in the V and the C and the S register. So it's just a regular summation. So 1 plus 0 is equal to, here's a 1, here's a 0. 1 plus 0 is equal to 1. Carry the 0. 0 plus 1 plus 0 is 1. Carry the 0. 0 plus 1 plus 1 is 0. Carry the 1. 1 plus 0 plus 1 is 0. Carry the 1. Okay, so I'm then looking at the carry out of the last stage. That gives me the C flag. All right, and then the V flag is the exclusive OR of these 2 bits of the carry out and the previous carry. So 1 exclusive ORed with 1 is 0. So the V flag is set to 0 in this case, and the sum is 0, 0, 1, 1. All right, straightforward enough. Let's do one more example for m equals 0. All right, so for m equals 0, I'm taking the A register taking the B register, add those together. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, carry the 0. 0 plus 1 is 1, carry the 0. So it looks like my C out is a 0. And then my, let's put that in the wrong spot. C out is a 0. And my V flag is 0 exclusive ORed with 0. So that's also 0. I'm missing both spots. I want this to go in the blue. Okay, and then the sum register is 1, 1, 0, 0. All right, so there's two examples where m is equal to 0. Let's scroll down to where m is equal to 1. I've already typed in the results here, but let's verify these two cases. All right, so when m is equal to 1, what I know is I'm subtracting b from a. All right, and so the way we do that subtraction is we complement b, so we get the b bar, and then remember that we put the carry in to the first full adder, set that equal to 1, so that gives us effectively an addition. And so we're taking what is in effect the 2's complement of b. All right, so when I put b prime plus 1, I'm signifying that we're actually taking the 2's complement of b, and that's what's used in the addition circuit. All right, so what we do when m is equal to 1, we first do this step. Okay, so this step would be, all right, I look at 0, 1, 0, 0. I know that's a 4. 16 minus 4 is 12. And so what shows up in the B register is 12, 1, 1, 0, 0. All right, so from there, I add A and the B prime plus 1, the 2's complement. What happened there? And so I add that. 1 plus 0 is 1, carry the 0. 0 plus 1 plus 0 is 1, carry the 0. 0 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. All right, so I see that my carry out was a 1. And then I have a 1 exclusive ORed with 1, which is 0. And then, of course, my sum bit matches. All right, so there's that example. All right, one more with m equal to 1. Let's go through it. Okay, when m is equal to 1, I know I'm subtracting, so I need to take the 2's complement of 1, 0, 0, 1. 1, 0, 0, 1 is 9. 16 minus 9 is equal to 7. So the 2's complement is 0, 1, 1, 1. So now I take this and add it to this. 0, 1, 1, 0 plus 0, 1, 1, 1. Add those together. 0 plus 1 is 1. Carry the 0. 1 plus 1 is 0. Carry the 1. 1 plus 1 plus 1 is 1. Carry the 1. 1 plus 0 is 1. Carry the 0. So I look at my C flag. Let's go back to blue for that. My C flag is a 0. And then my V flag would be 0 exclusive ORed with 1, which is 1. All right, I take the sum, put it into here. All right, so that's how you do the calculations for the expected result table for Lab 5. I've got a Canvas quiz set up for that where you can do 6 more of these example calculations just to make sure that you know what to expect with this circuit.